This video is an introduction to matter waves. This includes everything but the Heisenberg uncertainty principle, which we are going to look at separately. So previously we looked at the photon, and we saw that we could treat the photon both as a wave and a particle, and we thought that was such a good idea that now we're going to treat anything that has energy and momentum as having a wavelength. So we're saying any particle that we have also has an associated wavelength, which we find by using the de Broglie wavelength formula. So we're going to take this equation here and say the de Broglie wavelength is equal to, well, we'll call that lambda. That's equal to Planck's constant h divided by the momentum p. So if you can find the momentum for a particle, you can find its associated wavelength. And in some cases, you might find it more useful to use hc over pc. So you can read more about that in your book and in the OpenStax physics textbook. Next, we're going to look at Bragg diffraction. So if you remember, at the end of Physics 261, we looked at double slit interference, which we're going to do in this section also. And you can read on the bottom of page 3 about Bragg diffraction. And in this experiment, there were a beam of electrons directed at a crystal of nickel. You can look at the diagram on the bottom of page 3. So you have the beam of electrons coming down at an angle from the surface, theta, and then reflecting off of the first layer and the second layer. And that can cause interference over here at the screen. Now, these two waves are coming from a source. Remember what we did in Physics 261. These waves can't really be parallel if they're both coming from the same source, but if the source is really far away, they're approximately parallel. And then they're going to meet somewhere over here. You could put a screen here like we did in lab for the double slit experiment in Physics 261. And you have an interference pattern at that screen. If the distance, if the difference in the distance that the two waves travel from here, which would be coming from this wave going down farther before reflecting and bouncing back off. So the path length difference here for on just this side is d sine theta, but since we have to go down on this side and then back up on that side, it would be twice that. So we have the path length difference here. And if the path length difference is an integer number of wavelengths, then we have constructive interference. So our formula for Bragg diffraction is the path length difference 2d sine theta, and that's equal to n times lambda. This is also similar to the thin film interference that we looked at in Physics 261. So d is, and you can read this on page 4, is the distance between adjacent crystal planes called the lattice spacing. So that's the distance here. N is an integer. And theta is being measured from the surface here. So the two extremes would be if theta is equal to 0, and then the beam's coming in like this. If it's coming in like this and going out over here, well, if the waves are really going parallel to the surface, they're never going to meet up again over here, but the path length difference would be 0 since they're just traveling horizontally. And that would be when theta is equal to 0, we get sine of 0, so that would be when n is equal to 0. The other extreme is when theta is equal to 90 degrees, and that is when the light's shining straight down. When theta is equal to 90 degrees, on this side of the equation, we just have 2d, so that difference would just be going back down a distance d and coming back up the same distance. So there's our formula for Bragg diffraction. And then we have the double slit with matter. This experiment works the same way that the double slit experiment worked in Physics 261, but now with matter waves instead of light waves. So our equation here is d sine theta times n lambda, where the path length difference is d sine theta and n is an integer. And you may want to go back to your Physics 261 book for the derivation. For the double slit experiment, we have d sine theta, the path length difference, is equal to n times lambda, where n is an integer for constructive interference. Now, they do something on page 8. Now, this is actually for a single slit, not for a double slit, but the principle is the same. So we may need to use some of these equations here, which we learned about back in Physics 261. Okay, so for everything that we've done so far, as long as you have the equation and you know what to plug in, you should be good. So doing the problems here the problem shouldn't be that complicated. You need to know how to figure out what type of problem it is, but then you're just using the formula. Similarly, for the thermal wavelength, you can read through the derivation on page 6 and on page 7. You can calculate the thermal wavelength, which is for an ideal gas sample at a known temperature. And so this would be, instead of doing the de Broglie wavelength, if you have an ideal gas, the thermal wavelength can be found, and that is by taking Planck's constant times c divided by the square root of 2 times pi times mc squared. So this depends on what type of gas it is. And then times k and times the temperature T. The temperature must be in Kelvin. And K is Boltzmann's constant. This is given to you in the appendix. Now, the one thing that you have to be careful of is that we had a different physical constant K in Physics 161, which was Coulomb's constant. Usually in this course, the constant K is Boltzmann's constant. You can't always tell just by looking at the equation, but if you're doing something with the electric field, the K would be Coulomb's constant, and that's in the emission spectra lab. So when you're doing that, it's Coulomb's constant, and I don't know that Coulomb's constant is used for K anywhere else, but here we have Boltzmann's constant, and we can look that up in the appendix. And that's it for our introduction.